I'm going to talk to you about, going all in on HTTP3 and QUIC. So yes, as mentioned, I am Daniel Stenberg. I started my journey with HTTP back in 1996, actually. So I've been working with HTTP client code for a long time. I founded and have been working with curl since 1998, and I work on it full time these days for Wolf SSL, where I do commercial support for curl. I've also been involved in the organization IETF since maybe a dozen years or so. And that IETF is then the organization behind the protocols that I'm going to talk to you about today, both HTTP3 and QUIC. So here's what we're looking ahead to today. Then I'm going to start to talk to you a little bit about HTTP 1 and 2 and why we're going to 3, some of the problems that we've had along the way and that we're trying to solve with going to number 3 now. And HTTP 3 is a protocol done over the new transport protocol QUIC, and this I'll get into why we need QUIC and a little bit how it works, and then how HTTP 3 is that HTTP protocol over QUIC. There are some challenges to do this or to deploy this, and I'm going to run through a bunch of them and a little bit about the current situation with the deployments and how we can try out HTTP 3 today, and something, maybe a guess on when we will see this coming true live on the internet. Maybe soon, maybe not so soon. I'll get back to that. So I'll do all the questions and answers at the end. So if you have questions, I know that you can submit them during the talk, and I will certainly try to get through all of them in case whatever I miss or say, hit me with your questions and I'll get to them in the end. So HTTP is that protocol that started back in, the world looked like this basically. HTTP 1 was, the spec for the HTTP 1.0 came in 1996. Then HTTP 2 came in 2015, and now we're already talking about HTTP 3. So certainly an accelerated time schedule here for new and improved HTTP versions. Just to get everyone on the same track here, HTTP is the protocol that looks like this, basically. We've all seen it, used it. Most of us, I would hope, many of us at least, are familiar with it. You do a request, you send headers, you get a response with a response code, and you get headers back and the content. This is how we deliver the web to browsers, and we do APIs, and a lot of things are doing HTTP these days. So everything, of course, starts with HTTP done over TCP, the fundamental transfer protocol. TCP is the very old transfer protocol that was the first RFC for TCP actually was published 1981, so we're approaching 40 years here for this protocol. It's a very basic protocol. It sends packets over IP. It establishes a connection, three-way handshake, ping, pong, ping, and we have a connection. It sends data to the other end, and it makes sure that the data ends up in the other end or the connection fails. So it resends lost packages, and it delivers a reliable byte stream. I tend to view the TCP then as this chain link in my image here as a set of individual links that are sort of tied together, the links being individual IP packages. And everything is in clear text, so there's no protection for TCP, right? So everyone can snoop on your TCP data on your network, and they can also impersonate servers or whatever. There's no security and there's no safety, no privacy. That's TCP. But we're talking about HTTPS these days, and HTTPS is TCP and TLS then, and HTTP over that. And just to make sure that we are also on the same page here, the number of web pages done over HTTPS, this is page loads done by Firefox over time. So done with HTTPS then, and not HTTP. HTTPS being the secure version then. So we can see that the trend is clear that we're having a gradual increase over time. Now, most of our requests or page loads are done in HTTPS, and you see, as you can see up right, we're above 80%, maybe 90%. We're climbing even more. So while we're not going to reach 100% any day soon. We'll certainly be very close to that. So basically the web today with browsers is HTTPS. The same graph, basically, split a little bit differently, split over platforms instead. And for Chrome, from Chrome, shows the data roughly the same. I draw a line there at the 80% level, so you can see that by 2020, almost all platforms are doing more than 80% web page loads over HTTPS. A lot of HTTPS, so HTTPS is the thing we're looking at here. HTTPS then has added security in the shape of TLS. TLS is the way we do added security added to TCP for HTTP1 and HTTP2. Transport layer security, that's the name, right? We used to call it SSL. Well, a lot of us still calls it SSL as well. So SSL, TLS, it's the same thing basically these days. So TLS, in most cases, adds more handshakes, maybe one round trip, maybe two round trips, a little bit of depending on your version and conditions. So the 3 round trip handshake from TCP, and we add 2 or 4 more round trips to get them up to a full handshake with TLS. So TLS adds privacy and security. Nobody can snoop on your traffic or read your data. They can't interfere with it or manipulate it, and you know that you're talking to the correct server. So you get all that, privacy and security with TLS. So that's what we want. So what we have here in the classic HTTPS stack that we've been using for so long is we have the IP, we do TCP over that, TLS on top of that, and then we do HTTP. This is the HTTPS stack. We're familiar with it. We've used it for over 20 years by now. So HTTP done over TCP started back, as I said, in the 90s, and HTTP 1.1 actually came in 1997 as an improvement to HTTP 1.0. And the biggest and the primary improvement from 1.0 to 1.1 was that it added support for persistent connections, that we wouldn't have to close the connection between the HTTP requests, which was a big benefit and made it much better than 1.0. So now we could reuse connections and it would become a much better protocol. But at the same time, or well, maybe not at the same time, but over time at least, the web and everything has transformed into a completely different thing than we had in the 90s. So nowadays we have a lot of objects. Websites have hundreds of objects, and to do this properly, or to give the users a good experience, browsers in particular then have started to create parallel TCP connections. Many of them in the standard way is to do 6 TCP connections per host name to do HTTP over, so that it could do a lot of parallel requests then, since that's what HTTP 1.1 is very serial. So we ask for a request or for a resource, we wait for it, we ask for the next and the next and the next, and we can sort of compensate for the problems by adding more parallel connections. This to the extent that it hurts the client so much that they have to close connections as well very often, since it now it needs to do a lot of parallel connections to the extent that it needs to close them very often to be able to have this many parallel connections to do the parallel transfers. Firefox data shows that the median number of HTTP requests done over TCP connection is 1, basically saying that it has to close connections very often, and it makes a very inefficient use of TCP because TCP is very slow in the beginning and gets faster over time. So by closing them, because it has to close them because it can't keep that many connections up, it also makes them inferior or not as good as they could be if they had been kept alive. It also, this many TCP connections also it causes the so-called HTTP head of line blocking problem. That is, we have a lot of connections and we're sending out HTTP requests over one of those connections. Even if you have 6 connections and you want to send out the next HTTP request on one of those 6 connections, it's a problem for the browser or the client to know on which of those connections to send the request. Similar to having 6 lines in the supermarket, how do you know which line is the fastest? Where are you going to bet your money on where's the trainee in the cashier, or which one has the troublesome customer in front of you. It's a complicated question. It makes it hard for the browsers to know how to do this efficiently. And of course, HTTP 1.1 is a node protocol, and browsers and users have created numerous workarounds around these challenges or problems to make sure that they can deliver a fair experience to users, like inventing host names for the same site so that browsers would create more connections, bundling many images within the same image, or putting resources into the style sheet so that you would download images at the same time, and a lot of other things like that. Creating bundles with all the JavaScripts put into a single file. All of those, I would say, funny workarounds or tricks that users did to improve HTTP 1.1 they were reasons taken into the procedure that then led to the creation of HTTP 2 that shipped in 2015, just over 5 years ago. It then encourages and tries to then go to one TCP connection per host name instead of 6, 12, 18, up to maybe sometimes 50 connections per host. It now says we should use one connection, and it actually tries really hard to make sure that browsers do that. Having one connection has certainly benefits because it makes sure that TCP gets taken advantage of to its fullest, so it gets up to speed much better, and we can much better really saturate the bandwidth in both directions when getting data to and from a remote server. It introduces then many parallel streams done over that single TCP connection. So that's how it does a lot of parallel transfers over the single TCP connection. That's an awesome thing when things are running smooth. And already by the time when this was shipped, we knew that it would create this problem called the TCP head of line problem, the TCP head of line blocking problem, which is when you're using one single TCP connection and you're doing a lot of parallel streams over that single TCP connection, and you lose a single packet, all streams have to wait for that single packet to get retransmitted, and then all streams can continue again until another packet is lost, and you have to wait for that single packet to get retransmitted to fix the TCP connection again, and then all streams can continue again. So a single lost packet can really hamper, well, hundreds of streams. Not an ideal situation. And at the same time, we've seen another trend. This is an ongoing trend that's been going on for a long time. We call it ossification, which is the thing where the network is learning what we're doing and we get stuck in time doing that. So the internet is full of tiny boxes or big boxes, or a lot of things like servers for routers, gateways, firewalls, load balancers, network address translators, everything like that. There's a lot of them, and they're all running software to handle network data. They're put in place to serve the networks in various aspects, of course, and they're all put there basically with the knowledge of how the network runs today, and it knows exactly how it's supposed to work today and not tomorrow. And these boxes, the middle boxes, tend to get upgraded a lot slower than the machines in the end. I mean, you upgrade your browser pretty much daily, weekly at least, or so. They upgrade all the time without you even having to do anything. You just run it and it'll update it itself in the background. And we even upgrade our servers regularly, maybe not as often as the browsers, but maybe annually or twice a year or something like that. While the boxes in the middle, they get upgraded much more seldom. So when they are installed today, they are installed there with the knowledge of how the network runs today, and they tend to not be very good at adapting to how the network changes tomorrow. It has the effect that, well, first let me show you a little, just an illustration. These are the middle boxes. Basically, that's me talking to the server, me in the upper left, talking to the server in the down right. Here's the network path through the internet. Those are the 4 middle boxes. They're not my boxes, they're boxes put there by operators or service operators. They're bindle boxes, they run software, they handle the network. Usually very fine, sometimes not as fine as we want it to be. I'll show you some examples. So ossification is the effect that whatever we do and that we seem to have a pattern, someone will take that pattern for granted and say that we will always do like this forever. This led to the, I would say, the discovery or a notion or realization that we couldn't do HTTP2, for example, in clear text over the internet, which is because if you do TCP on port 80, a lot of those middle boxes will sort of know, within quotation marks, air quotes, that we talk about HTTP1, so they will help our protocol to get better or fix it up if we do some mistakes, which then, of course, if we speak another protocol like HTTP2 instead, it'll just ruin the traffic. So it does this to an extent over the internet today that no browser ever really tried to make this work. I know one browser once expressed an intention to make it work, but they then later bailed out and never did it. One of the reasons why browsers never even try to do HTTP, well, they don't ship HTTP2 anymore, so they all do it over HTTPS only. Similar things like you can fix, improve things like in the TCP layer. And one of the primary examples here is the TFO, which is TCP fast open, which is an improvement to TCP to send data earlier in the handshake, to basically shortcut the handshake a little bit so that we wouldn't have to do all the 3 round trips before we can send data. We could send data already in the first packet, and then, well, we could potentially gain a lot of time, well, hundreds of milliseconds in the best cases. It turns out, of course, that there's too many machines out there or middle boxes that know how the TCP bits and in the TCP header are supposed to be, so they throw away packets that then set the little bits for TFO, making TFO not the fast open but very slow open in many cases then, so that it would have to retransmit the SYN packet instead without the TFO option set, and instead of having a faster open, it would turn out to be a slow open. This is a problem to the extent that no browser and no operating system have TFO enabled by default because of these intrinsic problems. Other things like adding a new transport protocol next to TCP and UDP is also, well, it's not impossible, but the problems with it have been deemed so big, so nobody's even trying to, mostly then, like, for example, your Wi-Fi routers at homes, they can all just run NATs and do address translations, for example, for these protocols and not for any other protocol. So in adding a new protocol to the stack is really, at this level, is really complicated. Sure, ICMP works too, but it's not a transfer protocol. So we stick to these 2 transfer protocols, and I'll talk more about that. Another more recent thing that ossification prevented was that someone invented a new compression algorithm for HTTP that was or is better than gzip in many cases. So yay for a better compression algorithm. Well, until you try to do it in clear text over HTTP, because then you realize that there are a lot of HTTP-aware middle boxes that know about HTTP compressions, and they will, again, help or destroy the traffic depending on what you do. So if you try to send broadly in clear text, a lot of these boxes would destroy the traffic rather than help you. So we only do broadly over HTTPS these days. Well, the browsers do. And in this similar way, then the ossification really prevents innovations and other future things that we could do, basically because these middle boxes, they have learned how we do things. They see patterns and they make those patterns sort of get stuck. So we're encrypting more. And by encrypting, we make everything opaque to the middle boxes. We hide the traffic through them, and they can't then draw conclusions and get stuck like this in time. So how do we improve or do these innovations in spite of this ossification? QUIC is one attempt to do this. And QUIC, I just have to add this, it's a name, it's not an acronym. It was an acronym once, but it's not anymore. Nowadays, it's just a name, so it doesn't mean anything. It's the name. And then someone will ask us, but why is it all in uppercase? I don't know. This phrase is actually in the spec, so it's the truth. So a lot of companies are involved and behind this effort in creating a new transfer protocol. Pretty much all the big data companies, the browsers and the CDNs and server operators, the big ones, they're all in this. So this is a new transport protocol, even though I said we couldn't create any new ones next to TCP and UDP. And no, we can't. So this time is HTTP 3 and QUIC is again built on experiences and experiments done by Google. They actually deployed this already back in 2013, and they created a protocol that back then was basically HTTP2 thrown across the internet in UDP frames. And they proved that it worked and it could actually improve performance and make things go better. And they showed that you could actually deploy this across the internet. And they have a widely used client. Chrome has a few users, and they have also a few very popular web services, so they were in an ideal position to run really wide-scale experiments and prove that you can do this without hurting users. And actually, gain performance and gain improvements. And they took this protocol to the IETF back in 2015, which, if you remember, was the same year then that HTTP2 was finalized. So it's the same time frame here. And I think possibly because it was at exactly the same year, it took a year until there was actually a QUIC working group formed within the IETF. And in 2016, it was created and it got immediately very popular and got a lot of focus from a lot of companies and people. And the IETF QUIC, which then uses the same name as the Google QUIC, which is a bit confusing, but it's now very different than the IETF QUIC is very different than the Google QUIC. And for example, the IETF QUIC was immediately split up into two protocols, the transport protocol and the application protocol. So that was one of the conditions. And some other things that the IETF said, we need to have this use TLS crypto and not the Google custom specific crypto, and some other things that made it that made changes to the protocol that nowadays makes it very different than the original Google QUIC, even if it continues some of the original ideas that Google tried out and proved that they worked. So when you change the transport protocol, you have a new chance to fix things. For example, you can address the problem with TCP line blocking problems by making sure that dropping a few packets won't be a problem to you. You can fix and do faster handshakes. I need to make sure that things are. So yeah, and you can fix faster handshakes. You can do earlier data that works. The things that I talked about, the TCP fast open doesn't have to be a problem anymore because now you can fix it from the beginning. With QUIC, we've also made sure that the connections are not terminated by a IP address. It doesn't have to be, so you can move it to a connection ID, which means that you can transport connections between network interfaces, for example, going from Wi-Fi to mobile data or to cable internet, Ethernet. You could just move over the connections easily, and the way maybe the internet or the networking wasn't really assumed to work back in the day. So by doing more encryption and always doing encryption, we make sure that you can do more things with QUIC. And of course, then make sure that we can do future developments even more. and possibly and hopefully not get stuck in ossification as much as before. QUIC is built on top of UDP. That's how it enables this to work without being a victim of the we can't do anything else except TCP and UDP, and this isn't anything else really on that layer. It's built on top of UDP. So TCP and UDP remain the protocols at that layer. And we use UDP instead of IP, basically treating UDP as IP, and we write a reliable transport protocol in user space here, just on top of UDP. So QUIC is similar and a little like TCP and TLS built into one. And I just then, of course, need to emphasize that UDP isn't reliable, but QUIC is. UDP is that protocol, which is connectionless. It doesn't do any resends. There's no flow control. There's no ordering. So there's just, sending data basically, and you can receive it if you can. But QUIC uses that layer, and as pretty much in the same way that TCP uses IP. So it adds connections and reliability and flow control and all that, and it adds security on top of that. There's always a secure version of QUIC. There's no clear text version of QUIC. Also then, QUIC has streams built into the transport protocol. And not only streams, but in the same way basically that HTTP2 did for HTTP, but now moved down into the transport protocol. And there you can actually then initiate them from either side, client or server, and you can do them either bidirectional or unidirectional, so a lot of different options, but primarily they are independent. So if you create, for example, if you would create two different streams over a single connection and you would lose one packet, if that packet would only belong to one of the streams, the other streams can go on and continue without having to wait for the resending that packet of the lost packet that only belonged to that particular stream. That makes them independent. They're in order and they're reliable, but they're independent between each other. Basically, that means that back when we do TCP, and for example, like in my illustration here, we have a green stream and we have a red stream. They come like this, intermixed over the TCP connection. If we drop a green one, the red stream has to wait as well until we can get the green packet retransmitted, and then both streams can go on again. While with QUIC, we can send them next to each other like this, the yellow and the blue one. And if we drop, for example, a yellow packet here, the blue stream can go on because the blue stream is still uninterrupted. So even if we drop several yellow ones, we just have to transmit those to get the yellow stream going. The blue one can continue independently of the other streams. And of course, that's all done then in the transport protocol QUIC. We will do then application protocols on top of that transport protocols. And those transport protocols like HTTP then get streams for free. And that could, in practice, well, in theory, be any protocol, and in the IETF work, it was mentioned already early on that could or should be DNS, and DNS and HTTP were the two ones discussed early on, even though DNS was postponed almost immediately, and we said we should focus on getting the HTTP out first. But there will be others. There's already discussions and talks about how to do other protocols and other forms of protocols over QUIC. So there will certainly be more as soon as this QUIC thing is shipped for real. HTTP done over QUIC is the first application protocol done over this new transport protocol. HTTP over QUIC is called HTTP 3. It's more or less the same HTTP we've known and learned from before, but adapted to be done over QUIC instead of TCP and TLS. So it's the same thing. We're a client, there's a server, we do a request, we send a method and a path, we send headers, we might send a body like in a post request. We always get a response, we get response code, headers, and body, all of this is the same. Same TCP, but different. So we we did HTTP 1 in ASCII over TCP. We introduced HTTP 2. We did binary multiplexed over TCP. And now we do HTTP 3, binary over multiplexed QUIC instead. Same protocol, done differently. Viewed as back to the sort of architectural overview. So I showed you from the beginning how the original sort of classic HTTPS stack looks like. We have IP. We do TCP over that, TLS, and HTTP 1 or HTTP 2. Nowadays, we instead go with UDP. We put QUIC over that. And as you can see, we then have a little TLS 1.3 box in here. And over that, we do the HTTP 3 protocol. And we put the streams one layer below than we did before. A lot of new things, UDP, QUIC, HTTP 3, and TLS 1.3 inside that QUIC box. Feature-wise then, HTTP-wise, HTTP 3 is very similar to HTTP 2. Different transport, and we have streams this time too. We can't do clear text anymore, only this QUIC, it doesn't have any clear text version. We can never do HTTP in the clear. We have independent streams now, which changes things a little bit. For I guess one of the most interesting effects this might have is that a server can, for example, send 2 images to the client, first image A, then image B, and they can actually end up arriving in the other order in the other side because they're independent. So we had to change the header compression algorithm, but it's basically the same, just adapted for the new QUIC world. Server push and early data is similar, but should work better now. We have much faster handshakes, which is then, of course, not really HTTP, but it's thanks to the underlying QUIC transport. And we are changing how we do prioritization, which I think is a known failure of HTTP 2. So it was never done we've sort of failed doing it in a good way, and it's being redone for QUIC and HTTP 3. So right now there's actually no priority at all, but it's being worked on, and hopefully it's going to be backported into HTTP 2 going forward. So will it be faster? Yeah, probably, and thanks mostly to QUIC, then it should be faster, since we get faster handshake, and we will hopefully get early data that works, so we can send requests and send data earlier in the handshake pretty much, so gain one or several round trips in the setup of connections. We have the independent streams, which makes connections and transfers much better, especially in lossy networks and bad networks conditions. So we should be much better then. But exactly how much remains to be measured, of course. We got data a long time ago from Google QUIC experiments, and we've seen occasional experiment data from people who have implemented different things with their experimental stacks, but there's still, I don't think there's not enough for us to actually show any numbers right now, and I don't think a lot of implementers want to show numbers, because right now it's mostly about developing and not showing performance numbers, or not anything they want to stand up and responsible for. So we are going to have to wait a little bit more to get the proper measurements and performance numbers. Okay, so how will we see QUIC and HTTP 3 then, in particular in the wild? It says https:// their URLs, we have them everywhere. And what is an https://URL? It is a pretty much implied TCP and TLS on TCP port 443. So maybe we need to connect to that using the old style of HTTP first in order to know about where we should talk HTTP 3. The HTTP 3 spec says that we do this using this new, it's not actually a new header, it's actually an existing header, but it's called alt service. And it's a header created back in the HTTP 2 days, which it's roughly the equivalent of this pointing finger. That server over there or that host over there runs the same thing as this server does, pretty much pointing over. And there's an alternative service hoster over there on that port number with that protocol or on that host name, and it will run there for this many seconds into the future, which is so you would, as client would talk to a server that then can say, oh, I also speak HTTP3 over on that host name for the next week, the next hour, the next year, or something like that. And then in the next request, when the client wants to talk to that server again, it knows that it has that information cached. So yes, it can talk to the HTTP3 server directly in the next request. Then pretty much losing a round trip before it can speak HTTP3. Of course, a browser or like that interactive clients, they will of course then possibly try to upgrade to HTTP3 in the background while talking the legacy version first. But there's also I would say the big possibility, or I think the expected outcome is that clients like browsers will just raise connections and try out. Will it work with HTTP2 or HTTP3? It might be faster than doing that extra round trip just to get that information. Probably going to be needed anyway to some sort of raising, especially if you, for example, close your lid to your laptop, you move your laptop to a new place and you open it up there because you don't really know if it'll work the same way there or not. So maybe the clients will raise TCP and TLS connections with QUIC connections anyway. And since QUIC connections verify the certificate in the connections always, you know that if you're doing this with HTTPS, you know that you can't connect to the wrong one by mistake anyway, since it's verified. What you could possibly do is connect to a server that isn't the correct one, and then of course it'll lose the race. There's also another work in progress called HTTPS DNS records, or RS, which is similar to the old service headers, but put in the DNS, so that a client can then figure out if it can try out HTTP3 already while resolving the host name, instead of trying that initial request done over a legacy HTTP1 or HTTP2 request. It can go directly to HTTP3. So, okay. That's all that. That's what QUIC is, what HTTP3 is, how we can upgrade to HTTP3. But okay, if we deploy this, will it deliver? And how will it deliver? There are some challenges with going with UDP, with a UDP-based protocol. For example, there's somewhere around 3 to 7%, maybe more, maybe less, than all QUIC connection attempts that will fail. These are numbers from Google and Facebook, and maybe when we go even wider, more deployments, these numbers will change, maybe up, maybe down. It's hard to say, but a lot of organizations and companies, they basically just block UDP because UDP has usually, recently over the recent years, been a source mostly for DDoS attacks and other problems, and used primarily for DNS or NTP, and easily blocked. And since the connections fail to this extent, clients will need to have fallback algorithms. So when it fails to connect QUIC connections, it has to fall back to do them old style, TCP TLS, basically, which also then is an incentive for some organizations to just keep the block, because clients and browsers will fall back anyway. To a server deployment, of course, a QUIC connection will look quite a lot like a DDoS attack, which is a challenge for deployment setups, how to handle all those QUIC connections. High-speed UDP has not really been done before over the internet. CPU-wise, QUIC is a really big challenge, since we see reports sometimes up to 2 to 3 times the CPU used to provide the same bandwidth data from a server, which of course is a lot. There are reasons for this, and some of the reasons is that we have really unoptimized UDP stacks, primarily in Linux. People haven't really paid attention to how to make sure that we do UDP effectively and CPU friendly. And we have really not any good UDP APIs to send a lot of data through UDP from user space. So there's a lot of user space, kernel space transitions all the time, unnecessary, which also adds CPU time and make it slower than it has to be. There's also a missing hardware offload, because doing crypto offloading with QUIC is done completely differently than done with TLS over TCP. So it all has to be done again, and hardware companies and network equipment companies are certainly behind in this. And we're only in the beginning of this. It's going to improve over time, of course, but right now the CPU hog situation is a challenge. Then there's a TLS situation that is also interesting. So TLS was made for TCP. It's a protocol on top of TCP to provide transport layer security. And just sort of when made like that, they designed it to send records containing messages. And each record can contain several messages, one or more. But since QUIC is not done on top of TCP, there was no use for these records. So instead, they designed QUIC to use TLS messages. Cut out the records, just use the messages, which was tricky because no TLS library supports this. Well, supported at the time when they came up with this. So since this was decided, of course, some of the TLS libraries have started to work on this and implemented it in their libraries, but still, it's a challenge for all the TLS libraries. And QUIC then also needs a few additional secrets because of it does more crypto than before. So basically, we have to upgrade and fix all existing TLS libraries if you want to use that TLS library to do QUIC. Just to visualize this records in the messages in records. So when you do TLS over TCP, you send record 0 and then you send record 1 and you send messages within them, like this perhaps. There's 2 messages in each record here. While when you do it in QUIC, you send just the messages. There's no TLS records. Because it's a framing layer, that's not necessary. So it made QUIC better and easier, but it sort of added a new requirement to the TLS libraries. And there's one TLS library that is bigger or more prevalent than any other, and that's OpenSSL, right? It's the world's leading TLS library used by a lot of software and applications and stacks everywhere. And they have officially postponed their work on QUIC or providing the APIs necessary to do QUIC until after they ship 3.0. And they have their public official policies that they will ship 3.0 in Q4 2020, which then means sometime late this year. But I don't know if that's going to hold. So QUIC work is going to start after that. And OpenSSL was already an issue when we shipped HTTP2 5 years ago, but then it was a big issue even though the latest version of OpenSSL supported the things HTTP2 needed. And it just took a long time until they had that bleeding edge feature in the version that most servers had deployed, pretty much in old CentOS deployments. And this time we're even further behind in that OpenSSL hasn't even merged, patched, not even into their master branch in Git. So we're certainly behind in TLS, at least in OpenSSL land. There's also a challenge that everything QUIC is in Userland. So all stacks are Userland and libs, and they all have different APIs because there's no standard QUIC API. So of course, we have to get married to one of those particular libraries when we write a stack or an application. And that's sort of, that's just a fact. And so you're going to hope you want to cooperate and work with the ones that you think have a long time and will survive and will be your best bet. And I don't think it will be moved into kernels anytime soon because QUIC is going to be a lot of code and a lot of crypto code, and we've seen such efforts before, and it takes a long time to get mode into kernels, if at all. So of course, there will be experimental builds and everything to do this in kernels, but official ones, I think it'll be a long time until that happens. QUIC is completely different than TCP, so we need a lot of new tooling. And of course, Wireshark is with us, so we're along the way, of course, and there's a new cool tool set for QUIC that's come up, which is QLog and QVIS. QLog is a standard logging format to log basically QUIC traffic and HTTP3 traffic in a standard way that a lot of implementations are now supporting, so they can write those logs client side and server side, and you can use the QVIS to visualize those QLogs to get a good graphical or visual overview of how the traffic runs. Pretty neat things to help you at the beginning now to actually to implement QUIC and HTTP3 stacks, but also help to, debug and hunt down errors in those stacks. So when will we see this ship? Potentially already in 2020. The specification and the working group is now in the called working group last call. So it is officially almost done, and we're trying to get all the details and all the errors ironed out and fixed. So it could potentially get down already this year. We'll see if things hold. There are a lot of implementations done. There's over a dozen, and most of them are open source, and you can find them done by this list of companies like Google, Mozilla, Apple, Facebook, Microsoft, Akamai, Fastly, Cloudflare, F5, Lightspeed, Apache, and more. So a lot of companies have spent a lot of efforts and invested a lot of powers here, and you can find them in all sorts of languages. So whatever you're fancy, you can go and have a play with them. And they do monthly interrupts, but most of them are participating in those, so to make sure that the protocols, the implementations are interrupting and they're working according to the specifications. A pretty good way to develop the protocol specs and the implementations hand in hand. So it works really fine. Right now, we can see implementations like this. So there are some bright sides. You can use curl, of course, to do HTTP3 today. You can now use the development versions of all the 4 major browsers, Chrome and Edge Canary, Firefox Nightly, and Safari Beta to do HTTP3. You can run servers like Caddy and Lightspeed or Nginx Tech Preview, or even the Cloudflare version, which is an Nginx patch run using Quiche to do QUIC. TLS library-wise, there are a bunch of TLS libraries that already support the QUIC stuff, but out of the bigger ones, the major TLS libraries feature-wise, Boring SSL and GNU TLS already have their support for the QUIC functionality in their APIs in current Git masters and recent releases, at least for GNU TLS. Boring SSL doesn't really do the releases. And Wireshark, as I mentioned, Wireshark are keeping up with the latest, so they've been on the track for a long time. What we haven't seen yet is that there's no support for Apache HTTPD. I don't think there's any work started at that yet even. And there's no IIS mentioned that I've seen. And as I mentioned already, there's no OpenSSL support for this. There's a pull request 8797 with a pretty mature and ripe patch for this that you can play with. So if you want to try to run HTTP3 yourself, you pop down one of these bleeding edge browsers, for example, Chrome or Edge Canary, and you use these command line options to enable it. They say H329, which is the 29th draft of H3, which is the current one. Or you can figure out, you can change the about:config when you run Firefox Nightly, or you can enter these settings menu when you run Safari 14 beta, I believe the number is, yes. So any of these, and you can, if you enable this in your browsers, you can go to these sites, for example, Facebook, Instagram, Google, YouTube. All of them run HTTP3 on their production service, really. So you can just use them as normal, and they might switch to HTTP 3. I think some of them don't run on all endpoints, so it might be a little bit of a hit and miss if you get HTTP 3 or not. But I think most of them do. When I've tried it, I've seen HTTP 3 responses to most of them, most of the time. With Cloudflare, I know you can enable it for your own endpoints if you run a server using Cloudflare. So there will be more and more of those also enabling HTTP 3. And I have this list at the URL at the bottom down with test servers for different HTTP 3 implementers, which, to be honest, is rather boring if you want to see something real, because they're basically just test pages showing static, boring content. And if you want to do it with curl, everything works with H329. So there's alt service support, and we can build curl with 2 different backends, ngTCP2 or with the quiche library. And we don't have any fallback yet. If it fails to connect to the QUIC connection, we don't actually fall back to TCP TLS yet, because it's tricky. I haven't really worked out how to do that. And if you actually try HTTP 3 in curl, this is how you do it. Basically, just tell it, well, this is the brute force way to do it. If you know that the site speaks HTTP 3, you just add -- HTTP 3, and it'll get a response. And it'll look exactly the same way as with any other HTTP version. Looking into the future, I think HTTP 3 will take some time to get sort of adopted and deployed because of the problems with all the challenges with server side with running this. And so it'll probably grow slower than HTTP 2 did. And some deployments, and I would have expected quite a few servers and service providers right now, they don't really see how they will get any benefit from switching to HTTP 3 short term. So some will probably just stick to HTTP 2 for a little while and see how things take off. But QUIC as a protocol is for the long term, and I think that we will see a lot more going QUIC over the time. So we will certainly go there, but I think slower. Looking into the future, we will see multipath forward error correction and unreliable streams and partial reliability and everything, because a lot of people are just waiting for QUIC v1 to ship, and then they will want to get on the bandwagon to do QUIC version 2, and not to mention a lot of new protocols done over QUIC as soon as QUIC has been established as a proper protocol. So there's a lot of new things looking forward to. And when I talk about HTTP 3, a lot of people then say, hey, I didn't say anything about WebSockets. And no, I didn't. WebSockets isn't really part of HTTP, so it's not part of HTTP 3 either. So this is not a fix for HTTP 3. There's no mention of WebSockets here, and it took a long time for WebSockets to get in support for HTTP 2. And that same way could be done for HTTP 3 as well, because it's using that similar method could be used for HTTP 3, but there seems to be very little interest for that. But instead, people are now talking about the new protocol called Web Transport, now taken over by the W3C instead of IETF, and it's said to be a WebSockets-like protocol done over QUIC. So that's where the work is now. So possibly we won't go to WebSockets at all for HTTP 3, but we will switch to Web Transport going forward. We'll see. I don't think we know for sure what's going to happen there, but that's where the development is right now. So rounding things up, HTTP 3 is coming, it's always encrypted. It's very similar to HTTP 2 feature-wise, but done over QUIC, which is then the new transport protocol which itself is done over UDP. There are challenges to overcome, and there's going to be interesting times going forward, and this might be done already. This says mid-2020. Maybe that is a bit over optimistic, but maybe before the end of 2020 at least. So thank you. That's what I wanted to tell you about, and I'm very keen at taking your questions. And if you're interested in reading more about HTTP 3, I wrote a document called HTTP 3 Explained at this site, so if you can go there and read. It's basically the text version of everything I said today. Thank you.
Oh, thank you, Daniel. That was interesting to hear, and it is nice. And well, can you please summarize, probably once again, but Vitaly asks, what are the, say, major differences between HTTP2 and HTTP3?
Well,
so far.
There's really not a lot of difference. If you're talking like from a application standpoint, the HTTP, that's very similar. But since the transport layer is completely changed, everything's binary over the wire is going to be different. So all the implementations that do HTTP3 have to be pretty much re-implemented or done, handled. So they have to handle this traffic. But feature-wise, seen from an HTTP perspective, they're very similar. Hopefully they will be better. I mean, in an HTTP3 world, we can do faster HTTP3 and they will do streams better. And so we will handle lossy networks better and so on. But the primary difference is that it changes the transport protocol, and that's not really visible in the HTTP layer.
Okay, I see. And going performance-wise, am I right that you said that performance is not to be compared at this point of time because the protocol is evolving and it is getting feature complete, so the implementations are not up to speed, right?
Yes, exactly. And I don't think they're rarely optimized for speed yet. So since they're mostly focused on interop and doing things by the working with each other and fulfilling the protocols and everything. So I think few of them actually want to, present their numbers and stand for them and be responsible for them because they haven't really tried to optimize for performance yet.
Okay, thank you. And do you probably know some benchmark that might be used to compare, say, end-to-end cases like protocols or web browsers, or end-to-end case for the end user, so they can kind of make a fair comparison between, say, HTTP1, HTTP2, HTTP3 to account the new features the protocol brings to their business case?
Right, and HTTP3 there is not going to add any new metrics there, right? Because if you, for example, if you run a website and you're considering should I upgrade to HTTP3 from HTTP2, then you will of course run your numbers exactly for your users like you would do before. So you would run one of those web performance measurement numbers and see if I switch my servers to HTTP3, will my clients experience a faster experience from the client side. And so hopefully everything will just be performed faster under the hood when you switch to HTTP3, and the browser will just show your site faster and in a more fluid way, and you will get your time to first byte and time to first all those different metrics are called, and so they will run them faster, and you will see that your site will run faster with HTTP3. But I think, as I mentioned, right now it'll be hard to. You will see the best performance metrics when you have the worst network connections. So maybe you will see this the best way if you're running, if you have a lot of users having crappy connections, for example, or connections that are far from your server, which usually is not the biggest servers or the ones with the most fancy connections or server setups.
Okay, and are you aware of any industry benchmark? For instance, for databases, we have TPCC benchmark, which can be implemented by different database vendors, and they can compete in, say, controlled environments. So we see which database performs better for the case that emulates kind of business-like workload. So I wonder if there is something like that for protocols.
Not to my knowledge, no. There's no established way to do metrics, but there's going to be. I've seen two metrics in the primary ones, and one is for example, people are going to use tools like there's a one called H2 load, which was very well used to implement when people implemented HTTP2 servers, which is basically just a tool that makes HTTP2 load traffic and measures how fast it can download HTTP2. And I think going with a single tool that can then exercise any server side, that is one way to do the metrics. And then I see a lot of implementers discussing just raw speed, how fast they can do quick transfers compared to TCP with TLS transfers, for example, on a single core in a controlled environment. But none of that they're not established, they're not standard tests. I just see them as possibly the most common ones when implementers are discussing their performance between each other.
Yeah, okay, I see. And that probably might need to involve like two parties for benchmarking the client and the server, because there are lots of features in the protocol and clients might fail to implement them, right?
Yes, exactly. And of course, then there's also more than, performance can be from many different angles, right? It also depends on, since this is also a transport protocol, you have to do congestion control properly, and you have to do a lot of different things that a transport protocol has to do, and you have to make sure that you do it right. So there's more than just performing bytes as fast as possible. You also have to do it in a fair way, and you have to handle it properly over time. Even also when the network changes and stuff like that. So it's certainly a challenge for everyone.
Oh, okay, thank you. I see. Oh, there is a traction in, say, UDP-based protocol implementation right now. So we have QUIC, we have RSocket. I'm not sure if you're familiar with it. Can you comment on like comparison between RSocket and QUIC?
Oh, I really can't. I'm not at all familiar with RSocket. But in general, when people bring up different UDP protocols, because this is certainly not the first protocol to be done over UDP. It's not even the first protocol to have streams for, within the connection, like, because examples like SCTP also has that, and even SSH has it to some extent, right? And HTTP2. So I think what makes QUIC different this time is the fact that they're addressing make sure that they handle the TCP. Well, the TCP had a line blocking problem, so that streams are independent, which for me at least is a pretty novel idea that I don't know of other protocols that have handled, and that they also make sure that they have a good security story, so that TLS and everything is handled properly within the protocol. But again, I don't know about RSocket.
Okay, I see. Thank you. That really sounds amazing. I mean, QUIC looks like a new TCP in that regard.
Yes, exactly.
Clarify if. Can you please clarify if there is a way to send unreliable stream within QUIC stream?
No, there isn't. You can possibly make up some hacky way to do it, but there is no established way to do an unreliable stream. But there is discussion about it. So, and I know there's a draft already written on how to do that for QUIC. So, as I mentioned, future things to work on with QUIC. I know certainly that people are very interested in doing both unreliable streams and partial reliable streams. So basically have retransmission only for a limited time, for example. That could be for sending video. Maybe you can retransmit a frame only if it's done within some milliseconds or seconds, and not if it's slower than that. And I think there's such a draft as well. So there's a lot of new work coming for sure. Once we have this framework that QUIC version 1 is, when that is established, there's going to be more of this coming.
Yeah, and there was a question from Sevolot that what is your suggestion for gaming kind of scenarios or teleconference scenarios? Do you think QUIC will evolve, or there will be some other approaches?
I'm pretty sure that people will do it over QUIC over time. Of course, I think right now I'm not sure because of all the challenges and sort of it's early days still. But I think the protocol is designed in a way so that it could become the single protocol to use for both the partial or the unreliable stream requirement, that's certainly a game requirement, right? Because in games, you often want both reliable and unreliable streams. So why not have them within the same protocol? And and it's also been mentioned often with WebRTC, for example, because WebRTC is already a protocol that is done almost the same way that QUIC is now. So maybe WebRTC as a video conferencing or chat protocol could be done over QUIC in the future. So I think we're going in that direction, maybe not immediately right now, but certainly in the future, yes.
Oh, I wonder, what do you think of DNS over QUIC?
DNS over QUIC was one of those first protocols that were mentioned in the IETF working group too. Certainly, we should make sure that DNS works over QUIC, and it's been mentioned several times. There are working groups in the IETF now discussing things like that. So, but then also in the meantime, since that was brought into the IETF in 2016, the DNS over HTTPS was also brought into the IETF and made a protocol after that. So maybe DNS over HTTPS is then the way to do it over QUIC, if that HTTPS is done over QUIC. I don't know. So we'll see. I'm sure that there will be discussions, and we'll see what happens.
Okay. I'm waiting while my home router could upgrade to HTTPS for DNS, and I get it would take a while to upgrade it to QUIC for DNS as well. That might take time.
Yes, it will. So yes, but that goes with everything that is QUIC, right? That it'll take a while until we'll see QUIC really take off. Since there are all those problems, the TLS libraries, all those CPU problems, the UDP problems, so there's a lot of things that have to be worked out, and then of course all those boxes and everywhere need to upgrade to software that can speak these protocols. So yes, it'll take time.
Yeah, and when we upgrade or create a new protocol, there is often a problem of having multiple protocols and negotiating the proper one. So you don't know if the server speaks HTTP3, right? You don't know if it speaks like IPv6 or IPv4 only. So can you please clarify what are the upgrade options, or what is the preferred negotiation option for HTTP3 clients?
Yeah, there's actually there are many answers to that, and it depends on a little bit how far into the future you're looking. And I think the way to do it according to the spec is the alt service response header, and that's so you have to have that response header on your old server. So you have to connect to it using HTTP1 or HTTP2, and that server has to respond with that header and tell you, I have my HTTP3 server over here, possibly on the same server, but you have to have that extra round trip and get the knowledge about that HTTP3 server. But then that requires that you connect to it with TCP and TLS. So which is, of course, it loses a round trip, and you need to have a TCP and TLS implementation in your stack. So if you would rather look in the future when you maybe want to upgrade to a world when you don't even have a TCP stack or a TLS stack outside of QUIC, how do you get knowledge about it then? And then you enter the world with having the DNS resource record. So you would have a field in DNS that says this server can speak HTTP3 over here, so you can get that information just by resolving DNS information. And then there's also, of course, just raising everything, try everything in parallel, try TCP and TLS and QUIC at the same time, which I'm sure a lot of people will do anyway, which then, of course, requires that you run HTTP3 on the same host name as you run HTTP2 or HTTP1.
Okay, yeah.
For me,
DNS.
for me, it's an interesting challenge with this alt service thing, which means that you pretty much have to cache the information that, oh, this server runs HTTP3 on that other site. You have to cache that information for, I don't know, a year into the future. That's really complicated in a world when you have a lot of applications that all want to do this upgrade, because how are you going to do that cache in a system-wide way? I don't think it's going to work. That's why I'm sort of hoping more on the DNS way to do it. But it's also complicated. So yeah, it's interesting times.
Okay. And can you please clarify what was the most tricky part when you implemented QUIC support in CURL?
One of the tricky parts is that since this isn't the implementation of QUIC is always done in user space, right? So we can't just wait for a QUIC socket. We can't pass around a socket and use that for everything anymore, like we could do with UDP and TCP. Then everything is abstracted away, and we have just a socket, and that's the API to the transfer. Basically, we just read and write to that socket, and everything else is abstracted away by the kernel. Now we need to create a UDP socket, and we have to have a lot of more context, and we have to add a lot of more sort of knowledge into the application. And we also need to then to do timeouts differently, because now the timeouts have to be handled by the application and not by the kernel. And we might need even very accurate, maybe even sub-millisecond timers and everything. So that it adds complexity. Most of that complexity I already had in curl, actually. So it wasn't that hard to add this into curl. I think we were pretty fortunate that we already had a rather complicated way to do this. So adding one more complication wasn't that hard. I think we're not completed there yet. So I don't think we've seen all the complications yet. So maybe it's a bit premature to talk about the most complicated things when we haven't done it all yet.
All right, folks. Thank you, Daniel, for your talk, and thanks, Vladimir, for assistance with Q&A, and thanks to our audience for great questions. So I remind you that there is a Zoom link where you can follow on and ask more questions to Daniel and Vladimir. So see you there around. Thank you. Bye-bye.
Thank you.
Thank you.